Let's embark on a journey across the wonders of our solar system and beyond, delving into three fascinating frontiers of modern astronomy: the flammability of Titan, Saturn's enigmatic moon, the gravitational lensing power of mighty Jupiter, and the ultimate limits of photon energy, as explored through the most precise astrophysical techniques of our age. Each of these topics pushes the boundaries of what we know about the universe, blending theoretical insights with the most recent and compelling observations. We begin with Titan, Saturn's largest moon, a world shrouded in thick orange haze, its skies heavy with nitrogen and streaked with clouds of methane. To the scientific imagination, Titan often evokes comparisons to early Earth, its organic chemistry hinting at primordial secrets. Yet, one question arises among both scientists and curious minds alike. How flammable is Titan, given its methane-rich atmosphere? On Earth, methane is a potent fuel. It drives stoves, powers industry, and, under the right conditions, can erupt in explosive flames. But Titan's story is very different. The key lies not just in the presence of methane, but in the conditions required for combustion. Methane, to ignite, requires a spark, and more importantly, sufficient temperature and oxygen. Titan's atmosphere is overwhelmingly nitrogen, with methane making up only a small percentage. Crucially, there is virtually no free oxygen, the vital oxidizer for fire as we know it. But there's more to the tale. Titan's environment is unimaginably cold, with surface temperatures hovering around 290 degrees, or about 179 degrees. At these frigid extremes, methane clouds float in the sky, and methane rains fill lakes and rivers. However, methane will not combust at such low temperatures. In fact, the ignition point for methane is above 161 degrees Off, or 107 degrees Cc, which is still vastly warmer than Titan's icy landscape. The absence of sufficient heat means that even if a spark did occur, the methane would stubbornly refuse to ignite. So, while Titan's atmosphere contains the raw ingredients for flammability in the form of methane, it is not, in any conventional sense, a fire hazard. Its air holds the promise of chemistry, but not the threat of flame. Explorers landing on Titan could marvel at its alien beauty without fearing sudden infernos. The moon remains a world of cold chemistry, not fiery catastrophe. A reminder that the universe often confounds our earthbound assumptions. From Titan's tranquil, frozen landscape, shift your gaze to Jupiter, the gas giant whose immense gravity shapes the orbits of moons, shepherds asteroids, and even bends the very fabric of space-time. Jupiter's mass, over 300 times that of Earth, gives it gravitational influence extending far beyond its colorful clouds. But did you know that Jupiter can act as a gravitational lens, focusing and magnifying the light and even slow-moving particles that pass near it? Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity. Massive objects like stars, black holes, and even planets warp the fabric of space-time, curving the paths of light and particles as they travel across the cosmos. We often think of lensing as the province of galaxies and massive clusters, whose titanic gravity reveals distant, hidden objects by bending their light into arcs and rings. Yet Jupiter, despite being far less massive than a star or galaxy, can also produce subtle but measurable lensing effects. Recent studies have explored this in detail. In 2013, researchers examined how Jupiter could gravitationally focus not only light, but also slow-moving particles, those traveling at speeds as low as 1,000th the speed of light, or 0.01 c. Remarkably, the Sun, despite its greater mass, cannot focus such slow particles with the same efficiency. Jupiter's unique combination of mass and size allows it to act as a lens for a broader range of energies and velocities, opening up new possibilities for studying dark matter, cosmic rays, and exotic particles as they traverse our solar system. In practical terms, astronomers are exploring ways to harness Jupiter's lensing power as a tool, using the planet's gravity to amplify signals from distant objects or to search for otherwise undetectable phenomena. The precision of these measurements is improving year by year, and as our observational techniques grow more sophisticated, Jupiter may become a vital ally in our quest to probe the farthest reaches of the universe. Finally, we turn our attention from the gravitational giants to the quantum realm, where the very nature of light itself comes into question. Photons, the fundamental particles of light, are massless according to the standard model of particle physics. This property allows them to travel at the ultimate cosmic speed limit, the speed of light, carrying energy across the void. But just how much energy can a photon possess? Is there an ultimate limit, a boundary beyond which even light cannot go? Theoretically, in the absence of mass, photons could have infinite energy. Yet, the universe sets practical constraints. At extremely high energies, quantum electrodynamics and the Planck scale come into play. Beyond this scale, the so-called Planck energy, around 1.22 on 10^19 giga-electron volts, the known laws of physics break down, and new, unknown forces may emerge. In reality, we have never observed photons anywhere near this energy, and the universe itself is not transparent to such ultra-high energy light. Recent research has taken a novel approach to exploring the properties of photons using the phenomenon of gravitational lensing. In December 2024, scientists analyzed gravitationally lensed fast radio bursts, distant, powerful flashes of radio energy that traverse billions of light years. By measuring the tiny time delays and flux ratios in these lensed signals, researchers have been able to place the most stringent limits yet on the mass of the photon. Their findings improved previous constraints by 1 to 2 orders of magnitude, confirming with even greater certainty that photons are either massless or possess a mass so tiny it is beyond the reach of current technology. These advances are not merely academic. Each new discovery brings us closer to understanding the true nature of light, gravity, and the fabric of the cosmos itself. Whether we are analyzing the chemistry of Titan, harnessing the lensing power of Jupiter, or probing the quantum limits of photons, modern astronomy continues to push the frontier of what is possible, guided by the ever-growing power of observation and theory. In the grand tapestry of the universe, every question leads to a deeper mystery, and every answer opens a new frontier. As we look to the skies, we are reminded that the search for knowledge is endless, and the wonders of the cosmos are limited only by our curiosity and imagination.